So Jacob is my student. I'm introducing Jacob Davidson, and I was just watching these talks, and obviously Dr. Kaminsky said this. We get so proud, like, to see this. But I was noticing themes, and what I was really reminded was that I first met Jacob when he took my astronomy lab class, and we worked with DS9 and image processing and these sorts of things. Like, they're the themes of some of the kinds of skills that these students are receiving. This is kind of fun to see. My story about Jacob and this project was that, and he might speak to this, but it's coming from work he's doing and particular technology, and saying, hey, work with this. But what was wonderful was the way that it came from him. It's his idea that we're going to study this technology, but we sat together in my office and said, what can you do with multiple wavelength lasers? And I won't give away anything here, but we designed something. We said, what if we did this, and what if we did this? And then we realized, oh, there's an industry based on our little musings in the office. So I was really pleased with the way that these students are learning the kind of science where they can make these discoveries themselves. So with that, let's give a warm welcome to Jacob Davidson.
All right, thank you, Dr. Severson. So my name is Jacob Davidson, and for my capstone research, I did dual wavelength laser photometry of particulate matter. So my research is applicable to air quality sensors and smoke detectors and improving their effectiveness. Analysis of smoke particles is important in both household safety and air quality management. This image shows the Tubbs fire in Santa Rosa back in 2017. Air quality sensors like the Purple Air PA2 dual laser air sensor incorporate dual laser systems to accurately determine the size and count of particulates in the air. And they were heavily used to map air quality during the recent fires. There are two main kinds of smoke detectors, photoelectric and ionization. Photoelectric detectors are more sensitive to smoldering fires, but they can be triggered by large amounts of dust. They work by shining a laser through a container filled with air. Once smoke particles get into the container, some of the light from the laser will get reflected, and there's a photodetector at a certain angle relative to the laser, which will pick up on the reflected light, which will trigger the detector. Ionization detectors are more sensitive to quick burning flames, but they can be triggered by burned food smoke. They work by incorporating a radioactive material in between two electrically charged plates, which causes a current flow between the plates. Once smoke enters the cavity between the plates, it disrupts the flow of current, which is detected and then will trigger the alarm. And the National Institute of Standards and Technology recommends photoelectric detectors over ionization detectors for their reliability. My research is very similar to how a photoelectric smoke detector works. So what is particulate matter? Typically defined as particles smaller than 10 microns, and they're extremely harmful to human lungs. The two main particulates I dealt with in my research are cigarette smoke and baby powder. Cigarette smoke particles range from 0.08 to 0.29 microns, and baby powder from 1 to 40 microns. This image here shows various particulate matter sizes in comparison to the diameter of a human hair. You can see the diameter of a human hair is typically 50 to 70 microns. So the particles I was dealing with in my research are much smaller than the diameter of a human hair. So light scattering occurs when a source of light passes through a scattering volume. Like I said, in the photoelectric smoke detector, the light will get scattered in all angles, and then you can place a photodetector or a power meter at a certain angle and measure the intensity of the light. Scattering due to particle size. There are two types of scattering, Rayleigh and Mie scattering. Rayleigh scattering occurs particle diameters around the size of air molecules, so 0.0001 to 0.001 microns. Me scattering dominates in larger particle diameters such as cigarette smoke and baby powder. Rayleigh scattering is the reason for blue skies, and it has a strong wavelength dependence. And Me scattering is a cause of white clouds, which have a low wavelength dependence. So jumping into my research, what I did was I took two lasers of different wavelengths, red and blue, and I first shined them through a container just filled with air to measure the intensity from the laser light. Then I would introduce particulates into the container and measure the amount of, measure the loss in intensity due to scattering by the particulates in the container. So as you can see here, this is the laser, and then I have a power meter there, and this is the container that would be in between those. And you can see the power meter would output the intensity typically in microwatts. So these images show how the light gets scattered due to the smoke particles. This particular example is from the cigarette smoke. You can see the light from the laser diode doesn't get scattered until it interacts with the smoke particles in the container. And then once the light exits the container here, you can see that there's relatively no more scattering occurring. And the scattered light causes a loss in intensity, which is measured by the power meter. And from this change in intensity, I was able to calculate the diameter of the particulates in the containers using the equation I is equal to I naught times lambda squared over 8 pi r squared. You can solve for the diameter, and with d is equal to 2 times the square root of I naught over I times lambda squared over 8 pi, where d is the diameter of the particles, I is the intensity of the laser minus the scattered light, and I naught is the intensity of the laser through the container with just air, and lambda is the wavelength of the laser light. So as an example, calculating the baby powder particle diameter, substitute in I naught is equal to 867 microwatts and I is equal to 2.1 microwatts, which are values measured by the power meter. And then lambda is equal to 690 nanometers, which is the wavelength of the red laser. You can solve for a diameter of 5.59 microns. So using that equation for various particulates like cigarette smoke, burned toilet paper, and baby powder, I was able to calculate average diameters of 0.34 microns for the cigarette smoke and 3.45 microns for the baby powder. I found that baby powder was the only case in which the red light scattered more than the blue light, and this is likely due to the greater average size of the particles in baby powder. So once you get further down the line on the Me scattering, side compared to Rayleigh, the wavelength dependence becomes less and less significant, and then on the smaller particle size like the cigarette smoke, there's a stronger wavelength dependence even though it's still relatively low. So taking my calculated average diameter of 0.34 microns and comparing it to a scientific study into the size of cigarette smoke particles, they found an average size of 0.29 microns, which is a difference of 17% compared to my calculation. Figure 1 here shows a scanning electron microscope image of baby powder particles, and you can, well, it's very hard to see. There's a size scale of 20 microns. And just analyzing the image, you can see particles ranging from 1 to 40 microns. So my calculation of 3.45 microns is within the range. Future work. One could take SEM images of the cigarette smoke and baby powder used in the experiment and compare the size calculations to the actual images. And then also analysis of smaller particles such as pesticides that are affected more by Rayleigh scattering. And I'd like to thank Dr. Severson and Ryan Brown for their assistance in this project.
Questions for Jacob?
Questions? Yeah.
So did you consider doing any differences in measuring it with like airflow, or I would think that particularly starting it out with the smoke in the air, a lot of it is like where that air is moving, and that's what we experienced in the Bay Area, like how the air in the pockets were moving.
Oh yeah, I didn't do any research into that, but that could be another next step into the next project for a student.
What was your favorite part about the project?
So I got to, as Dr. Severson was saying, I used a laser. The blue laser is a laser diode that I'm using in the company that I'm working for right now. And so it was just really good to get to know the laser, better, but it's helpful for work, so and lasers are pretty cool, so fun to play with.
All right, let's